You will need a compass to sketch circles and arcs for position analysis of mechanisms. So look for your compass from high school. This is the Staedtler half-pipe compass I used. This is available at Amazon. The bookstore also has inexpensive compasses. You can use any compass for the class. You can measure angles using a protractor. A straight edge helps draw clear illustrations and sketches. You can use any paper, but I recommend a black sheet of paper with no hole punches to give you freedom of expression and ability to scan and copy tray without worrying about paper jams. You can also use engineering graph paper with light grid lines. Ruled writing paper is not recommended for engineering problem-solving work. This is intended for writing essays, not making sketches and performing complex calculations. Here is an example of how you can use a compass. You can graphically construct an equilateral triangle using a compass. Stretch your compass to measure distance between A and B. Draw an arc centered at A. Draw an arc centered at B. Intersection of arcs defines vertex C. Draw lines between points defines a perfect equilateral triangle. Input motor drives rotation of crank arm. All four links in the mechanism are controlled by a single 1DOF input actuator. The wheel hub is a point of interest on the follower link. Kinematic skeletal diagram of mechanism showing links connecting rotational joints. Note the wheel hub is a point of interest extended beyond joint C on link 4. Points A and D are fixed points of rotation. Point C is defined by the intersection of arcs centered at B and D. Example of position analysis: rotate crank arm 60 degrees counterclockwise. Determine the angle change of the wheel hub length. The length of each link does not change with repositioning. Point C' is located by the intersection of arcs from point B' and pivot D. Measure angle change 26.4 degrees for follower link 4. Standard 4-bar mechanism. Input driver link 2 rotation about pivot A. Coupler link 3 in general motion both rotation and translation. Follower link 4 rotation about pivot D. 4 pin joint rotational degrees of freedom. 4 links equals 3 moving links plus 1 fixed frame link. Example of full cycle analysis of a 4-bar mechanism. Input link AB rotates full revolution driven by a motor. Determine position of all linkages during the complete cycle. For this example, link DC will rock back and forth between fully extended to fully retracted. The angle change of this follower link between the limit positions defines the stroke angle. Let's start with the fully extended position at B1 and C1, then rotate counterclockwise in increments. In the fully extended position, link AB and BC are in line and fully extend. We are now at the fully retracted position of the follower. Note the end of the input crank arm is now at position B2, and the end of the follower link is at C2. In this position, the link AB and BC are in line but overlapped. If we continue to rotate the crank counterclockwise, the follower link will now rock in the opposite direction. Side links move in pure rotation about fixed frame point. The motion of a 4-bar linkage depends on the length of the links in the mechanism. Possible motions are both side links can fully revolve in crank-crank, crank-rocker, and rocker-rocker. Other mechanisms such as a slider crank mechanism convert translation motion to rotation or vice versa. With the combustion chamber, the piston is driven causing the crank to rotate. For analysis, the important dimensions between joints are drawn in a skeletal kinematic diagram. The CAD details are not required. The piston is represented in the model as a slider to move up and down in the vertical direction. This is an example of an inline crank slider where the pivot of the slider is aligned through the pivot point of the crank arm. For an inline crank, when input crank arm rotates at constant angular speed, the slider moves with the same average speed in forward and reverse directions. There are 4 links when including the slider link and fixed frame. The links are connected by 3 rotational pin joints and 1 horizontal slider motion. The crank input link is in pure rotation. The coupler link is in general motion, both translation and rotation. The slider follower link is constrained to have translation motion only. The fourth link in the mechanism is the fixed frame upon which both the pivot of the crank is attached and slider moves. An inversion is for the piston slider to be the input link, causing the crank to follow. When the input crank arm rotates at constant speed, we can have the sliding link move with different average speeds in forward and return directions by including an offset between the pivot point of the crank and slider joint. The amount of offset can be used to control the speed of the quick and slow directions of the slider. Here is an example of an offset crank slider mechanism. The crank arm AB rotates counterclockwise in a full revolution. The slider will move back and forth between two limit positions. The links are shown in blue in their fully extended position at B1 and C1. The fully retracted position of the slider is located at C2. In the fully retracted position, the coupler link BC overlaps the shorter crank arm link AB. The displacement between the fully extended and fully retracted positions of the slider is the stroke. Let's start in the fully extended position and rotate the crank arm in increments. Here is another offset crank slider mechanism demonstrating displacement analysis. Point A is a fixed point of revolution for the crank arm AB. Point B is originally located 10 degrees from vertical. Point C is defined by the intersection of the arc centered at B and the vertical slider movement. The original position of the slider is found to be 8.46 units from the fixed position D. Now rotate the crank arm AB 15 degrees so that it is in new position B' located 25 degrees from the vertical. The new slider position C' is located by the intersection of the arc from B' and the vertical slider movement. The new distance of the slider is 7.04 units. Thus the displacement of the slider is the difference of 1.42 units in the downward direction. We have seen that primary connections between links allow either rotational or translational degrees of freedom, DOF. A slider with rotational joint can be modeled as two primary 1 DOF joints or one high-order 2 DOF joint. A hydraulic or pneumatic cylinder can be modeled with two links, an external cylinder link, and an internal rod with attached piston link. We can model the cylinder with three primary single degrees of freedom connections, two rotational joints at each end and one translational slider movement. A link can have more than two connections. Connections between two links are often called kinematic pairs. Another name for a pin joint connection is a turning pair. Be careful with three links connected on same pin. They can move independently as two turning pairs and thus allow two free degree of freedom motions. Kinematic skeletal model of mechanism only shows dimensions that influence the motion. Here is an example of a wiper blade mechanism. Points A and D are pivots attached to the fixed frame of the automobile. The shape of the links are not important to the kinematic position analysis, only the dimensions between connection points. The wiper blade moves as a rigid body together with the link 4. The triangle is shown to represent the link 4 rotating about pivot point D. The end of the wiper blade is denoted by point X and follows with rigid body motion with link 4. Here we recognize the mechanism as a 4-bar linkage considering the fixed frame 1.